So I want to finish this course by saying some remarks on Riemann Roch. So this is philosophical remarks and applications and some history and some more remarks about the proof and why it's a good result and so on and so forth. So maybe we could step back from the details of the argument I've been given and say why. So this is the first thing. Why do we want L of D? So so the point is this, that I might have C given as an algebraic curve, or I might have C given as a compact Riemann surface. So a Riemann surface, this is this picture that I've drawn several times, something like this. So this is a one-dimensional complex manifold. So this means every point has some kind of neighborhood like this, which is isomorphic to the ordinary ball in C. So in other words, locally I can take a complex analytic coordinate. And if I do the definition of, I'm not going into the definition of a manifold. If I took a different one here, then I'd get a different complex analytic coordinate, and I would require that the change of coordinates here is complex analytic. So everybody here has done complex functions of a complex functions of a complex variable in one variable, and this is just the natural context in which you do this. So I'm insisting compact here. So if you adopt this point of view, and this was really Riemann's point of view, you want to know, what can I do with C? And so so Riemann wanted to take, so let me call this guy sigma, to take sigma and embed sigma into PNC, and then prove and show that the image is an algebraic variety. Okay. So there's something quite a priori something which is surprising when you see it for the first time, namely this construction here. So this construction here, compact Riemann surface, this is something which takes place inside the complex analytic category. So this is, we're doing complex analysis, maybe we're going to talk about analytic continuation when I go round a circle, things like this. But we're just doing complex analysis. So we might think of, and so why is this an algebraic variety at all? And so, so Riemann says, well, you can't expect to have any globally defined holomorphic functions. If you ask for globally defined holomorphic functions, then there are several different ways of proving that that any such function is constant. And so you just can't do anything with constant functions, right? And so he says, well, let's take a few points and allow a few poles. So Riemann says allow a few poles. Right, so say D, let's just say sum of pi. It doesn't really matter. Eventually the pi's can coincide and I can allow multiplicities. Right, and suppose that L of D is a vector space of dimension L of D. The dimension equals L of D greater than or equal to 2. Right, then as soon as we do this, then I can take F1, F2, well, let me take F0, F1, and so on up to Fn. So the n is greater than or equal to 2. The n is greater than or equal to 1. And these now define a function. These now define a rational map, a meromorphic map from C or sigma into to projective space. Yes. So having just one of these functions is no good. I have one function, and there's nothing much I can do with it. Right? The function might be the constant, for example. If this is if I assume this is positive, then 1 is in LD. So we could always take F0 equals 1. Right, so I'm not interested in the case of only having one of these functions. I'm going to take several of these functions. And now, as I explained, this starts off being so initially, this is a rational map. It's only a rational map because it might happen that all of these guys, well, these are meromorphic functions, so certainly some of these guys take the value infinity, and it might also happen that all of them simultaneously are 0. Right? But we know that the theory of DVRs allows to remove the singularities. So I explained this already. Because this is a DVR, at any point P, I can multiply these things through by one common factor to make all of these guys regular near a point, and not all of them equal 0 at the point. And so I can remove the singularities. And so we've got this map. So let's call this phi. And so with luck, phi will be an embedding. Okay. So Riemann's original question is really very simple. A very kind of obvious question to ask. I've got this compact Riemann surface. What can I do with it? And the answer is I can try to embed it in projective space, and having embedded it, I can try to see it's an algebraic variety. So what do I mean by this statement, with luck? That's also not so difficult. So if you think about this map, F0, F1 up to Fn. So let's take these guys here to be a basis of LD. Okay, then phi is an embedding. Well, let's say phi is a one-to-one map. if and only if well, I want these guys not to map 2 points to the same. So I want phi of p not equal to phi of q, and this happens if and only if L of d minus p inside L of d has codimension 2. Right, this means exactly here some linear form in f naught up to fn is 0 at p and not 0 at q, and vice versa. And the different linear form is 0 at q and not 0 at p. Right, and so I take these 2 points on the I take these 2 points on the surface, p and q, and they get mapped in there. And so, you know, one thing that might very well happen is something like this, that p and q both get mapped to the same point. But if this happens, we're doing the map by means of these functions f naught up to fn. If this happens, this means exactly that all of the guys that vanish at the point p also vanish at the point q. And so in that case, this vector space has the wrong dimension. So if we know that L of d grows systematically with d, we can embed. We can use some L of d to embed sigma in Pn. And then, well, why is the embedded variety? Let me say, I explained this for the map to be 1-to-1. So similarly, phi is an embedding. Embedding means an isomorphism, a local isomorphism, of a neighborhood of P and C with its image if and only if L of D minus P minus Q inside L of D minus D has codimension 2. This is for all P and Q, for all P and all Q, including P equals Q. Right. So this includes a statement. If I have a point P here, I want to be able to find a function that vanishes here. So I want to find an x that vanishes at P with multiplicity 1, so that I want to find some linear combination here. X, a linear combination of the guys. Hey, you should have stopped me. It's when I say ridiculous things. It's so I want to be able to go down from L of D down to L of P and down to L of Q. Each of these subtracts 1, and they're different conditions. Right. So this here means that i.e. there exists a linear combination of the f's, of the fi's, that vanishes at p. To order 1. Right, so there's an element here in, so I'm doing L, now I'm doing L of minus 2p, L of minus p, d minus p, L of d. So first of all, I've got to have some element that doesn't vanish at all at p, then I've got to have some element that vanishes at p with order 1. Right, and then and then this is guaranteed not to be in there. So this is 1 and 1. So I use this passing from L of d to L of d minus p as part of the proof of Rimrock, but it's also part of the substance. It's also one of the things we want in applications. Right. So let me just say this: the image is an algebraic variety of dimension 1 because if I take the polynomial ring now, x0 up to xn, and I take the guys here in some degree d, in some my usual problem, I take some thing of degree m here, then this is a vector space of dimension. We know what this is. N plus m. Choose n. Right, but this is mapping now to L of m times the same d. So I'm thinking of mapping xi into fi in L of d, and then a monomial in the monomial xi to the power of mi product maps to product of fi to the mi. Right, and so we know that this thing grows linearly with as m times d plus a constant, so actually plus 1 minus g. Right, and therefore the kernel has to be quite big. So therefore the kernel here is I sigma. This kernel must be big. Right, so the Rimrock theorem at the same time guarantees that the image, if I take the Zariski closure of the image, the Zariski closure of the image is the variety defined by this, that will be a curve, and it'll be a curve having the same degree and the same genus as sigma, so it's actually equal to sigma. Right? So this part is easy, and I'm just sketching it. It's not important. Right, so I think this answers the question, why do we want this L of d? So we want it in order to be able to, so if C is already given as an algebraic curve, we want to understand the different possible embeddings of C into projective space. If C is just given as a compact Riemann surface, then we want to know that sigma is actually a projective algebraic curve, and so we can use the theory of projective algebraic curves to say something about these complex analytic curves. Right, so this is a little theorem here. This is a theorem saying we get, so this is a theorem. I'm not worrying too much about the proof. I'm thinking it's sort of basically obvious from the point of view of complex analytic geometry. This condition here this condition here with P and Q distinct points guarantees that the map is an embedding, and this condition here with P equals Q guarantees that the first thing guarantees that it's set theoretically 1-to-1, and the second thing here guarantees that at every point it's a local analytic embedding. Okay, so we can do quite a lot more with these ideas. So I'm going to talk about applications. You know, it's a sort of sad thing about giving any undergraduate course, any course at a preliminary level, that you spend a lot of time doing the theory and then you don't really have time for the interesting applications. So let me talk a little bit about the applications. And the applications are basically all concerned with this idea of embedding. So applications of Rimrock. And so we can start on this classification of curves. We can say what happens when g equals 0, g equals 1, g equals 2, etc. And here we run into this thing of hyperelliptic versus non-hyperelliptic. And then, you know, if we went on for another 10 lectures or so, there'd be quite enough to talk about. So let me say g equals 0. So I hope that you've thought about this in terms of the the homework sheet. G equals 0. This is on the homework sheet. So these are equivalent conditions. C is isomorphic to P1. So this is we're back to over a field K. Or there exists a D on C with degree of D greater than or equal to 1, and L of D equals degree D plus 1. And then g equals 0. Right, these are three equivalent conditions. Right, so you remember that the first thing we proved in Rimrock is that this L of D is less than or equal to degree of D plus 1. And so if that maximum is ever obtained, then necessarily the curve is P1 and the curve is of genus 0. So if you just think about this, so the condition 3 here certainly implies 2, because just take any point. P equals D, and then I'm going to have L of D equals, by Rimrock, 1 plus degree of P. Right. And so this condition 2, so a couple of sort of basically easy steps here. Use the D down to D minus P trick to get degree of D equals 1. Right. So assume degree of D equals 1 in part 2. Right. So what does this mean? It means that I've got this L of D equals 2 where D has degree 1. Right, and this means I've got an F0 F1 here. So I'm going to do this embedding thing. I'm going to use exactly this construction here. And so I'm going to use F0 F1 as a map, as a rational map phi from C to P1. So So I have f naught f1 in L of D. So what does this mean? This has got degree 1. So if I take you know, for example, C f0 plus D f1 linear combination, right? Then this has a divisor, div of C f0 plus D f1. This is a divisor, and it's greater than plus D is greater than or equal to 0. But this whole thing is degree 1. Right, so it's a divisor of degree 1, and also it's effective, and therefore it's a point. So this is 1 point P, depending on ratio C to D. Right, and you know, if I took a different linear combination, well, it can't be the same point, because otherwise all of these sections would belong to a smaller space. Right, so if I do L of D minus P and L of D minus Q, P not equal to Q, I must get different linear combinations. Right, and so this is saying, therefore this I get this map C to P1, and the map is 1 to 1. Right, so I've got a point P here, and it's mapping into C to D, and which C to D happens? Well, it's the ratio F0 to F1. It's also the unique thing, so that CF0 plus DF1 vanishes at the point P. Right, so it's 1 to 1. Why is it an isomorphism? Well, the C is an algebraic variety. It's embedded in some big projective space, and it's defined by some set of equations. Now I take this condition, CF0 plus DF1, and I ask for its divisors. That is a set of polynomial equations. It depending on C and F. And so therefore I've got a unique point of projective space defined by a set of polynomials that depends on C and D. Therefore this point P is a rational function of C and D. So P is a rational function. Sorry, I said that fast, and you have to think about it for it to make sense. It's a rational function of C and D. This is just because if I've got a set of equations that depend on, so it depends on the conditions of C, but those are fixed once and for all. The equations of C, that's fixed once and for all. Then it depends on these conditions C and D. So there's a point there, P, which varies with C and D, and it's a uniquely defined point, uniquely specified point, depending only on C and D, defined by algebraic equations, and therefore it's a rational function of C and D. So you have to think about it. I'm not saying this is completely obvious, but it is true. Right, and so therefore there's a rational map here, which takes C, the point CD to P1, and so there's a rational map there, a rational map back, and they're mutually inverse. Okay. So this was, of course, our starting example. P1 was related to the polynomial ring K of x0, x1, and the linear system's L of some m times the point at infinity is polynomials of degree m in one variable x, which is, for example, x1 over x0. So we've seen this many times now. This is the standard construction of algebraic geometry. The standard this is the standard linear system that exists in algebraic geometry. So finally, we get back to saying that this thing here is actually characterized just by these conditions. I've got a curve, a non-singular algebraic curve, and I've got a linear system here of dimension that much too much. So if I've got a, so for example, if C is isomorphic to non-singular conic in P2, we get now a rather abstract argument saying that C2 is isomorphic to P1. Right, so we go right back to, we can go right back to the beginning of the course and get the these kind of results they talked about in chapter 1 of the book as a consequence of a whole elaborate theory. Okay, now so let's go on to genus 1, and again here this really very neat description of the group law on an elliptic curve. So let me take C, a non-singular curve of genus 1, and you know, eventually I will need fix a point 0 in C. So what can we say? I want to say, given a divisor D a divisor on C, then Rimrock says L of D is equal to 1 minus the genus, so this is 1 minus 1 is 0, plus the degree of D. Right, and when is this true? True for degree D greater than or equal to 1. Right, this is the 2g minus 1 that I had in the as the equality statement of Riemann-Roch. So so what do I want with this? So let me. I haven't defined this yet, but at the beginning I defined what a divisor on C is some NIPI. Right. So there's a group div of C, right? And so that's the set of all these things, the set of all divisors. And this is obviously a group. I know how to add two divisors. It's the free abelian group generated by the points of C. Right? Inside here, I have the principal divisors. Right, so principal divisors is div of F, where F is in K of C. And I put not equal to 0 for hygiene. Right? So these form a subgroup. They form a subgroup simply because if I take the product or the quotient of two guys in there, I get the corresponding divisor is the sum or the difference of the two divisors. Right? And so this is, you know, that we can define the quotient. So I do div C divided by principal divisors. So this is the same thing as divisors of C divided by linear equivalence. I explained this. Two divisors are linearly equivalent if and only if their difference is a principal divisor. I don't know what's going on out there, but okay. So this is called. This is also called pic C, and I'm not going to explain this. It's called the Picard group. It also has other descriptions in algebraic geometry. Let me just take this now just as a piece of notation. So divisors, as I've said many times now, divisors have a degree. So there's a degree map here. So taking, and it goes to Z, and it's taking sigma and IPI into sigma and I. Right, so I can talk about div 1p to mean divisors of degree 1, and I can talk about pic 1 of C, pic 1 of, sorry, this is div 1, and this is pic 1 of C. So this is divisors of degree 1 up to linear equivalence. Okay, and I can also do things like pic. I can let me have pic I here, divisors of degree I. So let me say something. I'm saying things that are completely obvious here. I'm not. There's absolutely no content to this. This is just definitions and things that follow immediately from definitions. Right? However, we're going to get a good result immediately from this. So pic C is a group. Yes? This is it's a group here divided out by a subgroup. It's a quotient group. Right? And if I do pic 0, inside here I have pic 0 of C. This is also a subgroup. Right? It's just the kernel of the divisor map, if you want. At the same time, Rimrock for g equals 1 says that pic 1 of C is equal to C. It's in one-to-one correspondence with C. Why is this? Because if I have a divisor here, D, then in degree 1, L of D equals 1. One-dimensional. Right, so this means I can do, I can take D, so if I take an F in there, this is a one-dimensional vector space, so when I take an F, it's one element is a basis. It's defined up to scalar multiplication. Right, so I take something in this one-dimensional space and I write down div F plus D. This is greater than 0, and this is of degree 1. So it's a divisor of degree 1, and it's an effective divisor, so therefore it's equal to P. Therefore it's P in C. Right? So there's in other words, there's a one-to-one correspondence from points of C to divisors of degree 1 up to linear equivalence. Okay. So I'm setting out these statements here. You know, in a way that really does not need any proof. I mean, these things are really just obvious. The thing I've used here is Riemann-Roch for genus 1. Right? That's the only difficult point in this argument. The only point with any content. Right? And at the same time, C is, so if I do D and I go to D plus O, this is an isomorphism, is a bijection from pick 0 to pick 1. Yes, so this guy here is C, and this guy is a group. Right. So this is again. So you know, I should, if I was numbering these, this would be 1, 2, 3, and 4. These are completely obvious statements, except for this one that used Riemann-Roch. So the conclusion is, a curve of genus 1, together with a marked point, is a group. Has a structure of a group. So in chapter 2 of the book, I had all these games where I was doing this kind of thing, and then, you know, and so on. So in chapter 2 of the book. So what's going on here? So what's going on is that the difference of if L1 and L2 are two lines, then L1 minus L2 is principal divisor. It's a principal divisor on P2. It's the quotients. If I take the linear form defining L1 and the linear form defining L2 and take the quotient, then this is a rational function on P2, which has got a pole of order 1 along L1. A 0 of order 1 along L1 and a pole of order along L2. If I take this L1 restricted to C minus L2 restricted to C, this is a principal divisor on C. So you know, what do I need to do to make this curve into a group? So I take a point P here, I take it back into pick 0. So I have to think of the point P minus O. Right, so I'm just doing this D into D plus O. And that's what we were doing throughout this discussion of divisors on curves. Okay, so you know, we've done a little bit. We spent about 3 weeks developing the theory of Riemann-Roch, and then when we get to apply it in genus 1, we get back something which is very familiar, which is this group law on a plane cubic. This was a non-singular plane cubic. So remember, the statement there is, I've got a plane cubic curve, I've got a marked point O, then I say there is a unique group law so that P plus Q plus R is a constant. Right? So the group law is not take this point plus this point equals that point. It's, you have to do that and then you subtract. And what's really happening here is I'm working, if you work modulo linear equivalence, in other words, if you think of this something which is the difference between two lines as being equivalent to 0, then I can get from points P and Q to the point P plus Q plus R. To the point P plus Q in the group law. And that involves going to that point and then subtracting off 0. So the subtracting off 0 is exactly the inverse of this step. Okay, anyway, I mean, this is a very, very if you look at any textbook in algebraic geometry that treats algebraic curves, you will find this argument given after the proof of Riemann-Roch. It's just, this is a very substantial application of algebraic geometry that's used throughout arithmetic and other branches of geometry. So g equals 0 and g equals 1 are sort of exceptional. They're sort of, in a certain sense, easy. And, what do we get when genus is greater than or equal to 2? So in this case, we're going to get the canonical class, Kc. And the canonical class, we know, has L of Kc equals g, and degree of Kc is 2g minus 2. And the point I want to draw attention to is this g is greater than 2. So therefore, there is a map. There is a naturally defined map C into Pg minus 1. Right. So let's just think about this. Let's just think about this map just a little bit more. So I'm going to say. So let's look at. So let me take S naught, S1 up to SG in Kc. I'm sorry, S1 up to SG in Kc, a base in L of Kc, a basis. Yes. So I claim that for any P in C, there is a section. Then for any P in C, L of Kc minus P in L of Kc is not equal to the identity. This is not equal. So in other words, if I take these S1 up to SG, there's some magic divisor that I haven't explained very well. I'm going to explain it in a while. There's this S1 up to SG in this Kc, and they don't all have an extra 0 at P. So if Kc is an effective divisor, it means that at every point P, at least one of these guys has exactly the specified pole and no less. So I said a claim, so now I'm supposed to give a proof. What's the proof? Proof. So we ask the Rimrock Theorem. So ask Rimrock what is L, what is L of P? Right, so I've got this nice theorem that I spent some time developing, and I want to know what it tells me. And so I say L of P equals 1 minus G plus degree of P plus L of Kc minus P. So this guy is G-dimensional. There are two possibilities. This guy could be G minus 1, or he could be G, possibly. Right? And so this tells me this is equal to 1 if L Kc minus P equals G minus 1, and it's equal to 2 if this is G. Yeah, so I'm just doing arithmetic here. This is in this case, this kills this. Right, in this case, if I've got G here, then I'm getting 1 plus 1, which is 2. Right, trivial little piece of arithmetic. However, L of P equals 2 implies that C is isomorphic to P1. So this was in the discussion in, when I discussed genus 0. Right, and so this is impossible. Yes, and so we get this. So the conclusion is that this tells us something about this map to PG minus 1. So therefore, the map phi kc from C to P G minus 1 has the property that the pullback of the hyperplane section, is the whole of Kc, is Kc. So, here's this slightly awkward thing about curves, which is that we've got this map, and it's a rational map defined by f1 up to f. It's defined by these rational functions, right? And I can clear denominators. There's this removable singularities trick, which means that I can remove the singularities. So it means if all of those guys' SIs happen to vanish at some point, well, it wouldn't stop this being a morphism, right? Because I'd just cancel it. There's a removable singularity. That's like saying the function z over z can be continued analytically over the point z equals 0. Right? But the point is here that because these guys do not all vanish at a point P, there's no need to do that. And this map is actually given by the linear system Kc itself. Right? So I need this. So let's think about the case G equals 2. Then I've got C mapping to P1. Right? So this map cannot be of degree 1, it's of degree 2. So Kc, degree Kc equals 2. And what's happening here is that the map is of degree 2. The morphism phi Kc is of degree 2. Right? And so this says, so here's a picture, here's P1. I'm really thinking P1 over the complex numbers. This is a schematic representation. It's not at all a geometric picture of what's happening, right? It's certainly not a picture of the real line, of the real complex line. So the thing that's happening is here's my curve C. Right? If I were over the complexes, then the P1 would be a sphere, and this would be a sort of business like this. Right, so this is a variety of genus 2. I'm not drawing it very well, but the picture does show that there are 6 branch points. Right, so the curve C is so the curve C is genus 2 is given by how do I want to say this? It's given by y squared equals f6 of s1, s2. Right, I'm not telling you exactly which space this is defined in. You should think of this as y squared equals f6 of s, with s equals s2 over s1, and then extended over s2 equals infinity. Anyway, I'm not going to go into this. This is, but the point is that you know, what do I mean by the hyperplane KC is the pullback of the hyperplane section. So, you know, I'm in P1. What's a hyperplane? Hyperplane of P1 is just a point. So I've got to, if I take a point at P1, that point moves up and down the line. This is just the usual linear system on P1, which is O of 1, which is the, which is the ratio x1 to x2. So if this P1 is P1 of x1, x2, this is just the ratio x1 to x2. So if I take different linear forms in x1, x2, this point moves up and down the line. And then the inverse image of that, the pullback of this to the curve, is this divisor like this. Right? So this is a linear system of degree 2 that's moving in a non-trivial linear system. Right? So this picture also is going to appear in lots and lots of different places.